In this first learning outcome, we look at why numerical methods exist, when you'd reach for one, and the main techniques for finding roots and estimating areas. Let's get stuck in. Let's start with a simple question. Why do we even need numerical methods? The honest answer is that plenty of equations just can't be cracked with neat algebra. Something like x cubed minus x minus 1 equals 0 has no tidy formula for its answer, and lots of integrals are the same story. So instead of an exact solution, we chase a good enough one, using arithmetic that a calculator or computer can repeat in a flash to whatever accuracy we like. In this unit that boils down to two jobs, solving equations to find their roots and finding areas under curves. Almost everything in this unit follows one repeating pattern, so it's worth learning the shape of it now. You start with a sensible first estimate, x0, often by sketching a graph or spotting where the function changes sign. Then you apply a rule that turns that estimate into a better one, and you feed the new value straight back in, building a sequence, x0, x1, x2, and onwards. You stop the moment successive values agree to the number of decimal places you need. Let me get a few words straight before we go any further, because they'll come up again and again. Iteration just means repeating a process, using each result as the input for the next step. The iterative formula is the rule that does it, written x sub n plus 1 equals g of x sub n. And the two outcomes to watch for are convergence, when your estimates settle towards a single fixed value, and divergence, when they drift apart and never settle, which means the method has failed. Let's look a little closer at what an iterating function actually does. It applies the same rule over and over. You put in x0 and get out x1, you put in x1 and get out x2, and so the sequence grows. If it converges, the value it settles on, call it L, has a rather lovely property. It satisfies L equals g of L, which we call a fixed point, a value the function leaves completely unchanged. The word iterate comes from the Latin for to repeat, and that really is the magic here. One simple rule, repeated, closes in on the answer. Let's put that to work and estimate the square root of 2. We'll use the iterating function x sub n plus 1 equals a half times x sub n plus 2 over x sub n, starting from x0 equals 1. First step, a half of 1 plus 2 over 1. That's a half of 3, so 1.5. Feed that back in, and a half of 1.5 plus 2 over 1.5 comes to about 1.4167. Once more, and we get 1.41422, and again 1.414214. Just like that, the sequence has locked onto the square root of 2 to 6 decimal places, from a rule you could run on any calculator. Here's a neat way to hunt down a root without any clever formula, the change of sign method. A root of f of x equals 0 is just a value where the graph crosses the x-axis. Now, if your function is continuous and f of a and f of b come out with opposite signs, then a root has to lie somewhere between a and b, because a continuous curve simply can't get from below the axis to above it without passing through 0. From there, you keep narrowing the interval by decimal search or by repeatedly halving it until the root is pinned down as tightly as you like. Let's see that on a real function. F of x equals x cubed minus x minus 1. At x equals 1, we get 1 minus 1 minus 1, which is minus 1, so the curve is below the axis there. At x equals 2, it's 8 minus 2 minus 1, which is plus 5, comfortably above. The sign has flipped somewhere between 1 and 2, so a root must be trapped in that interval, and in fact it sits at roughly 1.325. Now let's zero in on that root to 2 decimal places, just by testing values and watching the sign. We know f of 1 is negative and f of 2 is positive, so the root's in between. Try 1.3 and we get about minus 0.103, still negative, while 1.4 gives plus 0.344, so now we're narrowed to between 1.3 and 1.4. Test 1.322, that's about minus 0.02, and 1.33 gives plus 0.023, so the root sits between those two. One more, 1.325, comes out just barely positive, which tells us the root is 1.32 to 2 decimal places, or more precisely 1.3247. It's worth being honest about when this method lets you down. It works beautifully when the function is continuous, there's exactly one root in your interval, and the curve crosses the axis cleanly. But it can fail in a few sneaky ways. A repeated or double root touches the axis without crossing it, so the signs are the same on both sides and nothing flags up. Two roots in the same interval can cancel out, their two sign changes quietly hiding each other. And a discontinuity, like 1 over x minus 2, can flip the sign across an asymptote, where there's no root at all. So always sketch the function first. Let's come back to iteration and turn it into a general tool for solving equations. The idea is to rearrange f of x equals 0 into the form x equals g of x, and then iterate with x sub n plus 1 equals g of x sub n. Take our equation x cubed minus x minus 1 equals 0. We can write x cubed equals x plus 1, and so x equals the cube root of x plus 1, which makes g of x the cube root of x plus 1. Now, here's the catch. The same equation can be rearranged several different ways, and some of them converge while others fly off to nowhere. What settles it is the gradient. You need the size of g dash of x to be less than 1 near the root. There's a lovely way to picture whether an iteration will work using a cobweb or staircase diagram. You plot y equals g of x and the straight line y equals x on the same axis. And the root is exactly where they cross, since that's the place where x equals g of x. Tracing the iteration draws a staircase, up to the curve, across to the line, and repeat. If those steps close in on the crossing point, you can watch the sequence converging on the root, which here is about 1.325. Let's actually run that rearrangement. We're solving x cubed minus x minus 1 equals 0 using x sub n plus 1 equals the cube root of x sub n plus 1, starting from x naught equals 1. The first step, the cube root of 2, is about 1.2599. Feeding that back gives roughly 1.3123, then 1.3224, then 1.3243. Keep going and it settles at 1.3247 to 4 decimal places. Notice how the steps shrink each time. That shrinking is exactly what convergence looks like. Now for the method everyone remembers, Newton-Raphson. It's a faster iteration that cleverly uses the gradient of the curve itself. The formula is x sub n plus 1 equals x sub n minus f of x sub n divided by f dash of x sub n. Picture drawing the tangent to the curve at your current estimate, where that tangent hits the x-axis becomes your next, better estimate. It usually converges astonishingly fast, roughly doubling the number of correct digits each step, though it can misbehave if the derivative is 0 or your starting point is poor. Let's picture that tangent idea on our curve. F of x equals x cubed minus x minus 1. Start at x naught equals 1.5, sitting on the curve. Draw the tangent there and follow it down to where it cuts the x-axis, at about 1.348, already closer to the true root. Repeat from that point, and the estimates come rushing in towards 1.3247. Each tangent hands you a far better estimate than the one before. Let's do the arithmetic. For f of x equals x cubed minus x minus 1, the derivative f dash of x is 3x squared minus 1, and we start at x naught equals 1.5. There, f is 0.875, and f dash is 5.75, so x1 is 1.5 minus 0.5 over 5.75, which gives 1.3478. Repeat, f of that is about 0.101 and f dash about 4.45, giving x2 of 1.3252. One more step, and x3 is 1.324718, already correct to 6 decimal places. 3 steps, where fixed point iteration needed 6 or more, and that speed is exactly why Newton-Raphson is so widely used. Let's switch tracks now, from roots to areas. Definite integration finds the area under a curve between two limits, but some functions just can't be integrated with a formula, so we estimate that area numerically instead. The trick is to slice the region into thin vertical strips of equal width, call it h, work out each strip's area, then add them all up. The trapezium rule gives each strip a straight top, while Simpson's rule fits gently curved tops for extra accuracy. And as a rule of thumb, the more strips you use, the closer you get. Let's take the trapezium rule properly. You approximate each strip by a trapezium that joins the tops of neighbouring ordinates, those ordinates being simply the heights of the curve at each x. The formula is h/2 times the first ordinate plus the last, plus twice the sum of all the ones in between. So the two ends are each counted once, and every value in the middle gets doubled. Because the tops are straight, the estimate is slightly off wherever the curve bends. Let's estimate the integral of 1 over x from 1 to 2 using 4 strips, so h is 0.25. The true answer, for reference, is the natural log of 2, about 0.6931. Our x values are 1, 1.25, 1.5, 1.75, and 2, and the heights, 1 over x, are 1, 0.8, 0.67, or 0.5714, and 0.5. The two ends add to 1.5. The three middle heights sum to about 2.0381, and we double that. So the area is 0.25 over 2 times 1.5 plus twice 2.0381, which works out at about 0.697. That's close, and just a touch too big because 1 over x curves upwards. Simpson's rule is a real step up in accuracy. Instead of straight tops, it fits a parabola through each pair of strips, so it hugs a curving graph much more closely. The formula is h/3 times the first ordinate plus the last, plus 4 times the odd-numbered ones, plus 2 times the even-numbered ones in between. Because it works in pairs, you need an even number of strips. And for the same effort, it's usually far more accurate than the trapezium rule. Let's redo that same integral 1 over x from 1 to 2, 4 strips, h equals 0.25, but this time with Simpson's rule. The heights are the same, 1, 0.8, 0.67, 0.5714, and 0.5. The two ends add to 1.5. The odd ones, that's 0.8 plus 0.5714, come to 1.3704, and we multiply that by 4. The single even one in the middle, 0.667, gets multiplied by 2. Putting it together, 0.25 over 3 times all of that gives about 0.693254. Compare that with the true 0.693147, and it's far, far closer than the trapezium rule 0.697. Whenever we estimate, we ought to say how good the estimate actually is, and there are 2 ways to measure that. The absolute error is simply the size of the gap, the approximate value minus the true value, ignoring the sign, and it carries the same units as the quantity. The relative error takes that absolute error and divides it by the size of the true value, giving a ratio with no units, which we often state as a percentage. Why does the distinction matter? Well, a 1 centimetre error is nothing on a motorway, but enormous on a microchip, and relative error is what puts it in context. Let's put numbers to it and compare our 2 integration estimates against the true value, 0.693147. The trapezium estimate was 0.697024, so its absolute error is the difference, about 0.3877. Divide that by the true value, and the relative error is 0.059, which is 0.56%. Simpson's estimate was 0.169324, so its absolute error is just 0.107, and its relative error works out at 0.154%. Simpson's rule is roughly 36 times more accurate here, and that shrinking percentage error shows it plainly. In practice, you'd almost never grind through all this by hand, and a spreadsheet is perfect for the job. For iteration, you pop x naught in a cell, write the iterative formula just below it and fill down to generate the whole sequence in seconds. For integration, you list your x values and heights in columns and combine them with sum using the trapezium or Simpson weights. Scientific calculators have equation solvers and numerical integration built in, and graphing tools like Desmos and GeoGebra let you see the roots and areas, which really helps you pick a sensible starting value. Let me talk you through the sort of formulas you'd actually type. For fixed point iteration, if x sub n sits in cell A1, you'd write A1 plus 1, all raised to the power of 1/3, then fill down. For a Newton-Raphson step, you'd type out x sub n minus f over f dash directly, referencing A1, and fill down again. To list your heights, you just compute 1 over x for each x in the column, and then the trapezium and Simpson totals are weighted sums of those heights, using the h over 2 and h over 3 patterns we've already met. Fill down, and the machine handles all the repetition for you. Let's gather it all together. Numerical methods give us good approximate answers when an exact solution is impossible or simply not worth the effort. An iterating function repeats a rule, x sub n plus 1 equals g of x sub n, to build a sequence that can converge to a root. You can locate roots by a change of sign, as long as you watch out for repeated roots and discontinuities, and you can refine them with fixed point iteration, or the much faster Newton-Raphson. And to find areas, the trapezium and Simpson's rules do the work, with absolute and relative error telling you exactly how well. So that's the whole picture for this outcome: why numerical methods matter, how to find roots by iteration, change of sign, and Newton-Raphson, how to estimate areas with the trapezium and Simpson's rules, and how to judge your accuracy with error. If you'd like to go deeper, the reading list points you to solid textbooks like Stroud and Bird for the engineering maths angle, alongside journal articles on teaching these very techniques. For something more hands-on, the Desmos and GeoGebra links let you play with roots, tangents, and areas on screen, while the worked case studies show these methods solving real problems. Do take a look before you tackle the assignment, and remember the submission and support details are all there on the slide.